From here to the stars, I am your host, Stephen Euin Cobb. Our guest today is Dr. Rebecca McCauley Rench. Dr. Rench is a program scientist in the Planetary Science Division at NASA headquarters. Thank you, Doctor, for taking the time for this interview.
Oh, happy to do so.
Okay, thank you. First of all, give us an overview of the successes of the Mars Curiosity mission.
Well, Curiosity actually just had its anniversary, its landiversary of about 11 years on the surface of Mars. And in those 11 years, it's done a fantastic job of exploring Gale Crater and giving us a really deeper understanding of what sort of environments existed on Mars a long time ago. And Curiosity is the mission that has told us definitively that at one point in the past, Mars had a habitable environment. So we know that there was liquid water on the surface of Mars. We can see that in the features that we see with the Curiosity rover, with the cameras we have on board and with the scientific instrumentation we have. So that's pretty amazing to tell us that it was a habitable place. That's definitely been a question in astrobiology for decades now. And then it's also told us a lot about some of the organic chemistry on Mars. Mm-hmm. So we have an instrument on board Curiosity called SAM, the Sample Analysis at Mars. And that's an instrument that is able to take the sample that we drill on the Martian surface and put it through some chemical transformations and tell us something about the chemistry in the sample. And so with that, we've been able to tell that there are these organics in the surface. And it's also been able to tell us some interesting things about the carbon isotopes of those organics. And very interestingly, the carbon signature of what we've been seeing on Mars is very different than the carbon signature of what we see on Earth. We don't know yet why that's so different. There's a lot of hypotheses on why that might be different. But either way, it's fascinating because it tells us that there's interesting organic chemistry going on the surface of Mars.
There's some confusion, I believe, between the Curiosity mission and the Mars 2020 mission. If you would clear up the confusion by contrasting the two.
Yeah, so they are related. They are very much sister missions in many ways. Curiosity came first on the surface of Mars, and it's been investigating Gale Crater for, like I said, about 11 years. It was such a successful mission, had such an awesome payload that we, NASA, decided to use a lot of that heritage that we found in Curiosity to build the Perseverance rover, Mars 2020. And so that has only been on the surface for I'm probably going to get my numbers wrong here, pandemic years, but it's been there for about 3 or 4 years at this point. And it's in a different place. So it's in Gale Crater, and it has a different main mission. So Curiosity has been very focused on understanding Gale Crater and past habitability and exploring that at Mars. Mars 2020 Perseverance has been focused on collecting samples for Mars sample return. So that's bringing samples back, hopefully in the next decade or so, so we can actually do some Earth-based laboratory work on those samples. We can have just a lot more resources available to us if we bring samples back. So Perseverance is more focused on that. It does have some similar instruments available to it in terms of the cameras and the lasers and the way that it can drill, but it's got that sample cache that Curiosity does not have. It also has a tech demonstration, the helicopter Ingenuity, which has been just very cool to see in action. That's our first powered flight on the surface of another planet. And we're really getting to see how beneficial having something like that, a drone, a reconnaissance, can be in a science investigation. So they definitely build on each other. They have some different objectives. They look very similar if you're, especially if you're building your Legos with the two. But they also, are there at different times, and they're at different craters on the Martian surface.
You mentioned there is evidence that there was life on Mars long ago. Do we have a sense of if it was definitely there and maybe how long ago?
So I didn't say that there was life. What I
Okay.
said was that Mars was once habitable.
Okay.
And so what that means is that it had the conditions that we think life needs to be able to thrive in an environment. So based off of what we know about life on Earth, which is our only known example of what life looks like, we think life needs water and that it needs certain elements like carbon and nitrogen, phosphorus, things like that in order to to thrive and have a cell and do metabolism. And so what we've found on Mars is that in the past, we are sure that it had the conditions that life as we know it would have needed to thrive on the surface. So it had liquid water, it had carbon available, it had, nitrogen and phosphorus and all of those elements that go into making life. So we haven't found evidence of life on Mars or anywhere else in the solar system at this point. But what we do know is that the conditions to support life were present on Mars early on. And we actually know that there's another place in the solar system, Enceladus, that currently has the conditions needed for life to survive as well. So that liquid water, carbon, nitrogen, phosphorus, all of those little pieces that life needs to get by.
It's not in my questions, but I'm curious, just what would we need to find on Mars to say absolutely there was life on Mars? Would we have to find something that can be rejuvenated like a living cell or something?
Yeah, I mean, so that's actually something that astrobiologists are trying to figure out. So we had the Viking mission back in the 1970s, and that had some life detection experiments that were developed based off of our understanding of life at that time. We actually have learned a lot about life since then, including discovering life in the deep sediments of our own oceans, which we didn't know back in the 1970s. So we have a much better understanding now of, what it means to be life and what we're looking for. But it's hard. It's hard to kind of find an unambiguous signature of life. And that's actually why a lot of the astrobiology community has been developing what we call the ladder of life detection, which is trying to bring together enough information that's all related to answer the question kind of conclusively on whether or not we found life or not. So that starts with finding a habitable environment. And then you kind of build on it by looking for maybe molecules that you would only suspect for life to make, and then looking for maybe sort of maybe a redox or a chemistry reaction that you would only expect for life to have. Or and basically what you do is you want to have life be your very last hypothesis. So it's, whenever you've said, okay, I can't figure out any other way that this sort of chemistry or this sort of molecule would be present here unless it was life that made it. And that's what we're looking for. So it's really not just one piece of information. Obviously, if you saw you saw an animal run across, you're like, okay, well, that's life. But that's not really what we're looking for. What we're really looking for are the microbes. And we're also trying to make sure that we keep our minds open to both life as we know it from here on Earth, but also trying to extrapolate that to maybe life as we don't know it and make sure that we're trying to detect that as well.
Does NASA have any plans or proposals for a human mission to Mars sometime in the future?
So NASA's working on getting humans to Mars. That's the whole beginning of Artemis and the Moon to Mars campaign. That's what we're preparing our astronauts for, and we're looking at architectures that can put boots on the ground at Mars. Right now, I think most of the estimates are out in the late 2030s, 2040s range for when that might happen. But right now, we're really focused on getting people back to the moon and using that as a testing ground and preparation for going further out.
The soil samples collected by Mars 2020, what is the potential for a future mission to return them to Earth?
So that is what the Mars Sample Return Project is all about. So we have a whole group at NASA. I'm actually not part of that group, that is working on figuring out all of the pieces and steps along the way to make that happen. It includes figuring out how to make a Mars ascent vehicle. We have folks out at JPL that are working on, how do you lift off from the surface of another planet, right? Which is a pretty amazing feat to think about, sending a rocket off of a planet like that, especially with the larger gravity well than the moon. Also thinking about the planetary protection requirements of bringing those samples back, and how do we do that in a safe way that also preserves the integrity of the science in those samples, right? We want to make sure if there's anything in there that's biological or potential contamination, we want to make sure we contain it, but we also want to make sure we can study whatever's in there and not just destroy it. So we're looking at that, and we're looking at a sample receiving facility that would be the place where those samples would go and be analyzed and worked on. So there's a lot of pieces to it. Oh, and then there's the fetch rover idea, which is basically getting a rover onto the surface of Mars to go pick up the samples, get them back to the Mars ascent vehicle. So all of those architectures are actually still being looked at in terms of exactly how it will all piece together, who the partners are that are going to be doing all of the pieces. It is an international effort, and exactly the timeline on which it might happen. So it's definitely in the works. It's in the plans. Perseverance was the first step in Mars sample return, and so we'll just continue down that path.
Describe, if you would, how the Mars Reconnaissance Orbiter and the Mars Odyssey Orbiter participate in the process of sending information from the landers back to Earth.
Getting information back from the surface of Mars is not the same as opening up your computer or getting on your phone to scroll social media. It takes a lot more. There's not a GPS network or internet at Mars. So what we need to do is we need to get the data from the surface assets into orbit, and then relayed to the deep space network, which are the big dishes we have around Earth that can communicate with our missions, our planetary missions throughout the solar system. So pretty much all of the orbital assets at Mars have some relay capability. And what we do is we figure out when they're going to be in the best position to receive the signals, and we set up all of the surface assets to send the signals at the right time. We coordinate that across all of the surface assets, right? Because we've got Perseverance, we've got Curiosity, we have lots of things going on at Mars. So we plan exactly when those things are going to come back, and then they relay it over to the Deep Space Network, which we also coordinate because it's also receiving signals from other planetary missions that are further out in the solar system.
Sounds like a complicated process.
It is. And we have amazing engineers and technicians that make all of that work, and really wonderful teams of people that are so collaborative in making it work, because every so often something doesn't happen as you think it will, right? Putting a spacecraft out there, sometimes they have an issue, right? And they'll go into a safe, I think what we call safe mode, where the spacecraft or the rover is like, something happened that I didn't expect, and so I'm just going to go into safe mode and I'm going to protect myself until you can, start me back up and tell me, that everything's okay. And so those things are not unexpected in terms of, we expect them to happen, but they're unscheduled, right? And so whenever that happens, sometimes we need to work collaboratively across missions to get that relay time for those spacecraft, so that way we can get them back up and running and back on track for doing their mission. So, and everyone's really great at kind of coordinating that time and, giving a little bit of time that maybe they had reserved for their own mission, so that we can troubleshoot.
You are a program scientist for the Planetary Science Division at NASA headquarters. What goals do you work toward in that position?
A lot, actually. At headquarters, we wear a lot of hats. We cover a lot of different projects. Personally, my goals are related to astrobiology and really thinking towards the future of what astrobiology, space exploration looks like. So we have a lot of missions that are out there in the solar system exploring. Some of them are answering some great questions in astrobiology. But there are bigger questions to be asked in astrobiology, and so we need more missions to answer those questions about life on other planets and life outside of our solar system. And so actually one of my drivers, one of my personal drivers, is to think about what does it look like to search for life 100 years from now? And what could we maybe be looking for in terms of missions or a pathway to a mission that could get us there? And I really hope that maybe 100 years from now, we could actually send a planetary mission to another solar system and see maybe what a habitable world around another star looks like, and see if we can find anything out about life elsewhere in doing so. So far, we haven't done that, right? We haven't actually sent a spacecraft, and we don't currently have the technology to send a spacecraft out of our own solar system in that way. But I think we've got the engineering and the know-how to eventually get there. So my goals are to continue to push planetary science at NASA to get us there eventually.
You lead the Planetary Protection Research Program. What is the goal of this program? To protect the Earth, or all the planets in our solar system, or all the planets we will travel to during the coming centuries?
Yes, so planetary protection is all about making sure we don't contaminate other bodies in the solar system with Earth life, and also making sure we don't bring back any contamination that could be harmful to Earth's ecosystem as we explore. That's forward contamination and backward contamination that we're talking about. So a lot of what goes into that is making sure that whenever we send spacecraft out to planetary bodies that we think have some conditions where life could thrive and grow, that we're very, cautious in the way that we do that. And so we make sure that those spacecraft are very clean, that they don't carry any microbes on them that could go and proliferate on the surface of another planet. So whenever we send something to Mars or Enceladus, we spend a lot of time keeping those spacecraft really clean all the way until they're there. We also think about that on return samples. So I mentioned Mars sample return, how we're going to bring samples back, and how we need to think about, exactly what our process is going to look like in bringing those back so that everything is contained and secure while we get it into a facility, and kind of think about, maybe like a facility similar to what you might expect for pathogens like the CDC might have, where you would contain a sample in a very safe way while you were doing science on it. And then once we know that there's nothing in there that is harmful or potentially harmful, then we can release it and allow, it to kind of go to laboratories around the world. But the first looks on the sample, you want to do all of the analysis you want to do early on to make sure that it doesn't have anything that you should be worried about. Research funds work in learning about all of that. So it funds work in understanding how microbes can survive on planets other than Earth, how they might get distributed by processes on those planets like wind. It also supports development of technologies to help sterilize things. So how do you clean a spacecraft? Do you do that with really dry heat? Do you do that with hydrogen peroxide? Do you do that with a laser? There's a lot of ways that you can clean something and make sure that there's no microbes on there. But some equipment on spacecraft can be sensitive to those cleaning techniques. And so we try to kind of expand the ways that we can get things clean so that whenever we send them out, we know there's nothing there.
I myself am of two different minds concerning the sterilization of spacecraft. One is the Earth is full of asteroids that come from Mars. Something hit Mars through a rock and it landed on Earth. And I think it's like 3%, 2% of the asteroids on Earth. I may be off on my figures. I interviewed someone recently, about a year ago, that was an expert on meteorites. And the whole interview for a solid hour was all about meteorites. And And she covered Mars meteorites and lunar meteorites. But of course, she said, well, one of my questions was, does the Earth throw meteorites to other planets as well? And she says, yeah, well, we've got a stronger gravity well, but it happens.
Yes.
So there's a lot of cross-contamination, but still bringing something back from Mars, the stakes are really high. I mean, we just had a pandemic. And so, yeah, everybody would naturally be afraid of that. So it doesn't sound like the caution is overblown.
No, and getting more knowledge and information about the samples, right? That's really, really the key. So the way we can make informed decisions. And, I've definitely heard, the talk about meteors and meteorites and, the exchange of material across planets. And that's very true. It's absolutely true. It's also a very different mechanism, though, right? Because it's not like Mars sample return, for example. It's not going to take millions of years to get those samples back, or at least I sure hope not, right? Mm-hmm. But that's how long it would take for a meteorite to make it from the surface of Mars to the surface of Earth, right? So it's a very different kind of pathway to being deposited on the surface of each of the planets. And we all know that the space environment can be very hostile, right? There's a lot of radiation, it's a vacuum, water activity is very low. So there's a much longer period of time where a microbe would have to survive in those sorts of conditions to be transported in that way.
Mm-hmm. Plus the beginning of it
would on the couple year journey on the way back on a mission.
Yeah. Plus the impact, the original impact produces a lot of heat. So it's going to practically sterilize anything that it hits and sends off to the Earth.
Whereas we're trying to we treat it kind of like soft cushion landings and, mm-hmm. try to keep the samples as pristine as possible, mm-hmm. Rather than them just being like impact ejecta.
You are co-lead of the Habitable Worlds program. What are the goals of this program?
This program is one of our astrobiology research programs, and it's focused on understanding what makes a planet habitable. So what are the pieces of making a planet that makes it so it has those conditions that we said will support life as we know it? So what makes a planet have liquid water on the surface, and how does that change based off of the kind of star it's around, or based off of whether or not it's tidally locked to that star? How does its atmosphere change in those sorts of circumstances? How hot or cold can it be? How do nutrients get cycled, and how are they going to be available to life on a planet? So we have a really great example in Earth about a planet that is habitable. It has life on it. And there's a lot of really cool things about Earth, to be honest, like tectonics and our atmosphere and all of that. But trying to expand that and understand, out of the thousands, millions of exoplanets that are out there in the universe, how do we extrapolate what we know about the habitability of our own planet and some of the places in our solar system beyond, and search for habitable worlds around every star that's out there. So that's what Habitable Worlds is about. It's a lot of modeling work, actually. So trying to understand a process and then expanding that into various scenarios that we see whenever we look out into the cosmos around other stars, and try to identify, well, I think that planet would be habitable based off of, what I'm seeing in this spectra, and, what I understand about the mass of a planet and its distance from its star, and the star's composition, and maybe where it's at in the galactic plane, because radiation environment can change a lot based off of where you're at in the galaxy. So that's what Habitable Worlds is all about. Very cool.
You are the program scientist of the Planetary Data System. What is the function and value of this system?
So the Planetary Data System is where we put all of the data that comes back from all of our planetary missions. I actually like to say that it is the most valuable asset that we have, because whenever we get data back from New Horizons, from Pluto, or we go to Venus, or we go to Mars, or we go to Jupiter, we get all that data back. And the Planetary Data System's goal is to protect and preserve that data so that all future generations have access to it. And that, to me, is so important, because it takes a really long time to go to Pluto or to go to Jupiter, and to gather that data. And so if you don't preserve it and you don't make sure that it's going to be useful and accessible to future generations, why'd you send the mission in the first place? Because those future scientists, those future engineers are going to make new discoveries based off of that data that we have available to them that we can't even think about today. So the Planetary Data System serves that capacity. And it's not like, always super sexy to think about data in that way. It's a lot cooler to just think about like, the spacecraft out at, Pluto, and like, oh my gosh, it went so far, and it's, going out further into the interstellar medium. But really the product of that at the end of the day for the science community is the data. And all of the pictures you see, that's the data that comes back. And so that's what the PDS does.
I'm an archivist within my own family. I save the home movies and all the photos and stuff. And archiving things, the old information, is really important to me, and especially for NASA. Plus, in the early days of NASA, I think many missions didn't include budget for saving all the data, preserving it, infinitely, basically into the future. It's like, we ran the mission, we've completed it, we, put the stuff aside and lose the data. That sounds bad to me.
Well, and, we definitely see that there's been a lot of, as people have gotten better with computers and archival and including documentation with data so other people can learn about it, more open science, open data things, we've really begun to see so much value in just being able to share that data in a way that's totally open to anyone that wants to access it, rather than, stuck on the hard drive of some computer in some professor's laboratory, where, maybe no one will have access to it after they retire from the field. So, we keep pushing actually for more and more of our data to be accessible, and then also documented in a way that, anyone can figure out how to use it. And there's a constant push and a constant need to go back in the record and get that older data, off of those old tapes, and, off of the bookshelves and off of the stacks on the desks and out there and accessible. And so there's actually a program, I don't run it, but we have a program called Planetary Data Archival and Planetary Data Archival Restoration and Tools, PDART. And that is where we fund people to do that exact work. So to think about, improving data accessibility of our planetary data and improving the archive, and getting things in there. Because unfortunately, data can be lost if you don't go back and get it in time, because it will degrade on certain formats. And that's why archivists are so important in the whole process and making sure it's going to be available for future generations. Yeah, a lot of old formats, they were not permanent. Old tapes and old, stuff. Yeah, so yeah, excellent. Let me go I'm
to the
glad
next.
You can appreciate the archival. That's awesome that you do that for your family.
I spent 2 months digitizing VHS tapes of old family home movies. Yeah, it's a chore, but it once you've done it, then it's good forever.
Yes, exactly.
Because memory now is so cheap. It's
it is, and that's awesome, because it means it's more available to more people.
Well, we're at our time, so thank you, Doctor. It was great. You gave a great interview. It was great stuff. I appreciate it. That was Dr. Rebecca McCauley Rench. This has been From Here to the Stars, a video series created by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Join us October 12 to 15, 2025 in Austin, Texas for the Interstellar Research Group's 9th Interstellar Symposium. Learn more at irg.space. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.